starts off with the combustion of ethanol. We have ethanol reacting with oxygen to form carbon dioxide and water. Delta H is negative 1274 joules per mole. You guys could draw an energy diagram for that, right?
Yeah, I just don't want to.
It's going to look like, right? It'll look just like this, where that would be your delta H, negative delta H. Okay, are we asked to do that? I don't know, not on part A. All right, so part A says, it says, let me drag the question where I can read it. It is oxygen oxidized or reduced, and justify your answers based on the oxidation numbers. All right, so on the left side of the equation, we have elemental oxygen, and the oxidation number in pure elements in their natural form is 0. Y'all remember that?
Yeah.
And then on the right side, we have oxygen in 2 places. We've got carbon dioxide and water, and in both of those, the oxygen has a -2 charge. So here you've got a -2 oxygen and then 2 positive hydrogens. And then here you've got your carbon with a +4 and your oxygens each with a -2. So our oxygen goes from 0 to -2. Y'all liked oil rig better. Oh, there's another copy of Eloise trying to get in. Okay, so you remember this oil rig.
Oxidation is loss, reduction is
gain, and what we're losing,
that's the word.
we're gaining is electrons.
Yes.
So what happened here? We gained
Reduced because the oxidation number is an inverse of whatever it actually is. So like -2 means it's actually gaining 2, so it's reduction.
So yeah, because your electrons each have a negative charge, that means that your oxygens gained electrons. So yes, you're right on the money. So
yes.
Oxygen is reduced. Another thing to just keep in mind is that oxygen is an oxidizing agent, which makes sense.
Right. Almost always like a -2, right?
Yes, and the only time it's not is in hydrogen peroxide, where it's a -1, and that's a weird case for oxygen. But for these oxidation reduction, if something is an oxidizing agent like oxygen and things that contain a whole lot of oxygen, then it itself gets reduced. It causes something else to be oxidized. All right, for part B, we're asked to find moles.
Yes.
So yay, moles. Find the moles. Let me slide this where I can read it. So we are given a volume, a temperature, and a pressure, and asked to find the moles produced. Pivnert, right? We have our pieces.
I always forget about Pivnert. I tried to do that whole thing and then I totally forgot about Pivnert.
Okay, my advice to you guys is don't even try these without keeping your cheat sheets for each unit handy. I made copies of Hayden's cheat sheets and Kenzie's cheat sheets that I'm gonna put them in the little boxes in front of the school where you guys can pick them up if you want to.
Good idea.
Hayden, is that okay with you?
All good.
Well, they're so nice and neat, typed up, and they've got everything on them. So, and then I'm adding one of just lab questions for you guys. I made y'all a lab cheat sheet. So, but I'm going to put those together for it. They're not up there yet, but I'll get them together soon. Okay, so P, pressure in temperatures. 18.0 liters. N is our moles. R is your gas constant. 0.0821 liter atmospheres per mole Kelvin. And also, like, don't try to do your sheets with your problems without this sheet handy too. Right? Keep these handy. The equation sheets and your periodic table, because we need to be practicing the way you guys are going to actually take this test. All right, so N, R, and T. Well, okay, my gas constant has liters and atmospheres, so those match, and that's fine. Over moles Kelvin. Well, I need to change my temperature has to be in Kelvin. Right. So where's my calculator? So 273.15 plus 21.7. My temperature is 294.85 Kelvin. You may have used a different gas constant for this. Make your units in your problem match the units in your gas constant. This one is the easiest gas constant for me to remember, and I like working with atmospheres and liters. Anyway, all right, so solve that, and we get whoa.
0.76 moles.
I just hit something really weird. I gotta start over. Divided by, what was that, 24.03? Something like 0.77 times 18. Y'all, has it been so long that I can't work a calculator? 0.0821.
I can't work a calculator.
You better. All right, so 0.77. All right, what's going to happen on the AP exam if you write 0.77 moles as your answer for B and you don't show any work?
It doesn't get counted right.
It doesn't get counted right. So sadly, you gotta show some of this stuff. You don't have to show every single step, but you've got to show what you did. Or we can't
So
just.
they're essentially twisting our arm to make sure that we handwrite all of this.
You don't have to handwrite it. You can type it. The way that I thought you could upload your images, if you do handwrite it, doesn't work because it cannot be it has to be a JPEG or a PNG. It has to be an image file, and it cannot be a PDF. So you definitely need to practice it on that AP Classroom. And see. Any questions about that?
How can I make myself remember that I actually know how to do the problem?
So for me, I write down
Like I was just sitting there staring at all those numbers. I'm like, I have no idea what to do with these.
Okay, so if you got to start somewhere, right? So write down what's given, like 18.0 liters. You know that's a volume, right?
Mm-hmm.
So write that down. V equals 18.0 liters. T equals 21.7. 1.03 atmospheres, that's a pressure. If you label all these things, and then they're asking us, the question was, what are how many moles? And so, N equals question mark. If you write down a P, a V, and a T, and an N equals question mark, you're going to remember.
Yeah, Pivner.
You're going to remember Pivner. But if you just stare at the numbers, hoping something magically comes to you, that might not happen.
That's a fair point.
So, I mean, my advice is literally write down what's given and what you're looking for, and that hopefully that'll trigger your brain into which direction you need to go. All right, so let's try it on the second part, little double I. It says, what is the volume of methanol in milliliters? Whoops, C2H5OH. Okay, it's a weird question. What volume was combusted to produce that much? That's moles of CO2. That much CO2. And we have the density. So I can go. I can get grams of C2H5OH, and then use the density to change that from grams into milliliters. Right, they told us They told us that the density is 0.79 grams per milliliter. All right, so I'm not ready to do that yet. That would be after I find grams. How am I going to find grams of this? This B little I is just straight stoichiometry, right? So we're going to start with the moles that you just figured out in I. So start with your 0.77 moles of CO2. How do I change from moles of CO2 into moles of?
Use the coefficients.
Totally wrote methanol on here instead of ethanol. That's okay. Yeah, you use your coefficient. Let me fix my equation before I use it. All right, so for every 2 moles of CO2, I had to combust 1 mole of ethanol. So start with my 0.77 moles of CO2. For every 2 moles of CO2, 1 mole of ethanol, C2H5OH. Okay, now I'm almost there. Got to change it into grams, and then got to change it into milliliters. 1 mole of ethanol has how many grams? Let's figure that out real quick.
It'll be
46.07. So 46.07 grams in a mole. And I'm going to go ahead and squeeze my density in over here. I got moles of CO2 canceled out, moles of ethanol canceled out. My density for ethanol is 0.79 grams per milliliter. And I've got grams on the top here, so I need that grams to be on the bottom. 0.79 grams per milliliter. Now, everything cancels out except milliliters, right? Just worked my way through the units. And let's get an answer for that. 0.77 times the molar mass, 46.07, divided by 2, divided by 0.79. So I get 22.4 milliliters. All right, Zoe. Any questions about that? All right, so let's look at the next part. The next part says how much heat in kilojoules was released. So kilojoules equals question mark. How could I know such a thing?
kilojoules.
I got to go all the way back to my my given equation, where they tell us that the delta H is negative 1270 kilojoules per mole. So what that means is that 1270 kilojoules are released per mole of reaction. And so we could think about that as per mole of ethanol. We could stop, wherever we got to moles of ethanol. Our moles of ethanol was 0.77 divided by 2. We didn't stop there, we just kept going. But let's see how many moles that is. So 0.77 moles of CO2. For every 2 moles of CO2, there's 1 mole of C2H5OH. So it's half of 0.77, so 0.385 moles of ethanol. And we know this. For every 1 mole, there's 1270 kilojoules released. Remember that negative sign tells you the direction of energy flow. It tells you that that heat is released. That's what the negative means. So I don't really have to include the negative sign here because that word release tells me that it's going out of the system. So 0.385 times 1270 is 489. 489 kilojoules released. So we either have to put the word released in there or show the negative sign. I imagine they give you credit for that with or without the negative sign, because in the stem of the question, it says how much heat was released. So really, we should not include the negative sign, but if you do, it'll probably be fine. Questions about that?
How did you know to go do that? Like, how do you know to use the moles of CO2 and like go from there?
Well, I really just need to know the moles of like what I started with here, my ethanol, because that delta H tells me that it's in kilojoules per, it says on the worksheet, it says per mole of reaction. And so like if I worked this whole, if I combusted 1 whole mole of ethanol, if I did this full amount, like 1 mole of ethanol and 3 moles of oxygen, and then got out of it 2 moles of carbon dioxide and 3 moles of water, then that would have given off that full 1270 kilojoules. Does that make sense? Because I would have combusted the reaction would have been 1 whole mole of reaction of our ethanol that we started with. But I didn't have that much, and so really, however you figure out your moles of ethanol, that's really all you need. Well, I just went back to little II and figured it out like we did here. So take your 0.77 moles that we got in the first part, or in part B, and divide it by 2 because it's a 2 to 1 ratio here.
Okay.
What is it called?
All right, so C is a little bit different. This is the one that Ethan was asking about. Let's make sure we don't have anybody locked out. Okay, so C asks us for the final temperature of our air in our room. Okay, so our room is going to get hot when we do this combustion. And what's the final temperature of the air? So Eloise, where do you start if you don't know?
Write everything down.
Write down the things that we're given. So write down our givens and our unknowns and then go from there. So final temperature is what we're looking for. So that tells me I'm probably, when I see final temperature, I usually think Q equals MC delta T. Right? I think delta T doesn't show up in a whole bunch of places. But I'm thinking like I'm gonna take some air that I know the heat capacity of, and I'm gonna warm it up and see how much heat that takes. So let's see what we're given. We have a mass of air. Mass of air is given, it's a bunch. It's 5.56 times 10 to the 4th grams. Okay, so it's not how we usually measure the air in our room, but that's okay. You know how many grams of air are in your room?
Too many.
You could figure it out if you knew the density of air. All right. Originally at 21.7 degrees, what does that tell me?
That's your initial temperature.
That's my initial temperature. 21.7 degrees Celsius is my initial temperature. All of the heat says, assume that all the heat produced by the reaction was absorbed by the air and that the specific heat of air. So my C for air is 1.005 joules per gram degree Celsius. Okay, now we're getting somewhere. All of the heat released was absorbed by my air. So my heat released is MC delta T. Okay, I'm missing two of these pieces, right? Because the delta T is final minus delta.
Yeah.
Those flowers. Exactly.
No, I probably should, huh?
Yeah. Like it is there.
All right, so I don't know the final temperature. I also don't know the heat released. Where can I find the heat released? What you think? That's what we just figured out in the part before it. I mean, so many of our AP questions, they just get you to keep using the answers you got in the piece before it, right? So I have 489 kilojoules of heat released. Well, everything down here is joules. So I'm just gonna like quick change that to joules. And so my heat released is 489,000 joules equals, and then just plug it all, let's just plug it all into our Q equals MC delta T. So I've got my mass of air, keep your units so you can show that they cancel out. 5.56 times 10 to the 4th grams. My heat capacity of air, 1.005 joules per gram degree C. Now look, my grams have canceled out. And then TF, I don't know what you are. And then my initial temperature of 21.7 degrees Celsius. Okay, so once you get to this point, it's just do the algebra, solve for your final temperature. All right, so y'all ready to give it a shot? You try it, you plug it in while I plug it in, and we'll all get an answer. Five, six. All right, so we've got 0.875 equals TF minus 21.7. Okay, is this what you got? Somebody check me.
Hold on, my screen is kind of pixely. It's hard to see.
So I got 22.6 degrees Celsius. We heated the room.
Sounds good to me.
Well, somebody check me. So we heated up the temperature of the room a little bit, right?
A wee bit.
Almost 1 degree. All right. Any questions, concerns, comments? Ethan, does that help figure out that one?
Yeah, something like that.
Okay. And does our answer make sense? And look, because it's the heat released, we didn't include our negative sign here. If you get an answer, I mean, that doesn't make sense. Like if you did leave your negative sign here and you ended up with a
Take a picture of yourself with flowers and post it on the Facebook page and tag her or some such shit.
who's talking?
Let's break it up.
My mom.
So if you put
Oh, chemistry. Yeah.
if you had accidentally left your negative sign in here and you end up with a final temperature that's colder, then, and you would know that it did make sense, right? So
Yeah.
when you get to your final answer, try to think back, check back and make sure that it's reasonable with what the question is asking. You burned something in the room and you warmed up the room. So your final temperature better be a little bit higher than it started. All right, questions about that? All right, so we've got another part on D. Let's take a look. So for part D, they give us a method for producing ethanol. So C2H4 plus water. I see my equilibrium arrows. C2H5OH. And this one is also exothermic, but less. Negative 45 kilojoules per mole of reaction. So question D asks you to identify 2 ways that the chemist could change the conditions to favor the formation of more product. This question D is about equilibrium and Le Chatelier's principle. What are 2 things that you could do to make more product? What do you know about this reaction, first of all?
Things are reacting with water.
Is it endothermic or exothermic?
I'm gonna guess
Exothermic, because it's
No.
negative.
There is no guess. It's negative, so yes, it's exothermic. All right, so
That was wrong anyway.
if you have an exothermic reaction, then heat is one of your products. So every single time you see a negative delta H with a reaction, go ahead and write heat in as one of your products. All right, so you want to shift it to the right. What could you do? Did you come up with anything? It says come up with two ways. You guys come up with
What if we add a catalyst?
catalyst will get you there faster,
But it
but
won't give you more.
it won't give you more. So catalyst affects your kinetics, but not your amount of product. Any
I put my chemistry note sheet in a folder. So negative is in and positive is out.
negative is out, like exothermic.
Okay.
Heat is given off, so heat is a product.
Okay. Negative is exothermic.
Yes.
Got it.
What if we just add more reactant?
That would definitely work. That's a valid way. So one thing you can do is you can either, to make it shift to the right, you can do any of these things. You can add reactants. You
Or make
could,
hotter.
which of course adding more reactants makes more product, right?
Yeah.
But so here, that's going to be true. You can remove a product as it's formed. If you had a way to take this ethanol, was it ethanol or methanol? Yeah, ethanol. So take this ethanol and remove it as it's being formed. So remove the C2H5OH as it's formed. That's going to shift the reaction to reestablish equilibrium, right? We know it's at equilibrium because we have our equilibrium arrows. So it's going to shift to reestablish equilibrium, and the way that it's going to do that is by reacting more of these together to make more product. Okay. So another way, because we know it's exothermic, heat is a product, and so we could remove, what's it called if you remove heat? Cool it off. Right, if we lower the temperature of an exothermic reaction, we're going to push it to make more products.
Why does it make more products if it's colder?
Exothermic does, because heat is a product, and it's going to
So you're removing a product.
Yes, it's the exact same thing as removing your ethanol as it's formed. It has the same effect. For endothermic, this would be flipped, right? Your heat would be a reactant. And so for an endothermic reaction, you could make more product by heating it up.
It's like magic, but you can explain it.
It's like science and not at all like magic.
It's definitely like magic.
Okay. So I just came up with those three. You guys come up with anything else? So let's see what it says. It says, identify any two ways the chemist could change conditions. Oh, it says other than adding or removing. So we can't count these two. I still got to come up with one more way. So cool it off. I got another one in my mind. Do you guys have one? I'll give you a hint.
Did you change the pressure?
Yes. Who said that? Hayden?
Yes.
Good job. If you change the pressure, what am I going to have to do to the pressure? Because they're all gases, and so definitely pressure is going to play a role here. But on
increase pressure.
Yes. If you increase the pressure, it's going to shift to the side with the fewer moles of gas. So on my reactant side, I have 2 moles of gas. And on the product side, you only have 1 gas. So if you increase, oh, I smeared it. If you increase the pressure, it'll shift to the right. It doesn't always shift to the right. It shifts to the side with the fewer moles of gas. All right, now we have 2 that meet the conditions. So you guys see another valuable lesson there. When I reread the question, I realized we really didn't answer it all the way. So before you submit these things, double check it. Make sure we're answering the question that's asked. All right, so now we have 2 ways. We can either lower the temperature or we can increase the pressure. All right. Then we get to the part with the spectrophotometer. Is this what you were talking about? Somebody's.
Yeah. I said I didn't understand it.
All right. Come on, little focus. Okay, so this is like Beer's law. If anytime you see spectrophotometer or a colored solution, I want you guys thinking back to what we did with the when we dissolved the bullet casing.
Yeah.
And made the blue-green solution. And the higher the concentration, the darker the color will be, and also the higher the absorbance of light. Absorbance. All right, so this question? Somebody say something. All right, so this one is going from orange to blue-green. So we have an orange reactant, and we have a blue-green product. And we're you can determine the concentration of ethanol in the solution based on the reaction. So my ethanol is on this side, 3C2H5OH. It's just an alcohol, and so it doesn't have a color by itself, but it's in there with this chromium thing, 2R0207. That's your dichromate. 16H plus. All right, and then your dichromate changes into chromium 3 plus. We could answer all the redox questions about chromium if we wanted to. Plus some acid and some water. We don't care about all those other components, I don't think. Okay, so it's placed in a cuvette, placed in a spectrophotometer. The only thing the spectrophotometer can measure is the thing that's colored, right? So it's only measuring the color. It's only measured, it's really, if it's all blue-green, then we don't have any of our reactants left, right? But if it's all orange, then we would have more ethanol because we've also got more of the Cr2O7. And so by monitoring the color, we can monitor the shift of the reaction. All right, so we finally get to a question, and it says, the initial concentration of dichromate, Cr2O7, 2 minus, is 1 times 10 to the minus third molar. Calculate the concentration at 1.5. All right, so what is the concentration going to be? Okay, so the wavelength that we're absorbing it, there really is a lot to think about in this question. I'm not surprised if it got you a little bit flustered. But you remember how when we did our Beers Law lab, we had to choose the wavelength for those things that had the highest absorbance? And then if that number goes up, that means we have more of that thing. And if the absorbance goes down, then we have less of it. So what's happening, just looking at the data, y'all can't see the data table, but what's happening to the concentration of the dichromate over time?
It goes down.
It goes down. It drops down to, and it's supposed to be a linear relationship. So let's see. Absorbance of 0.78 absorbance goes with a concentration of 1 times Cr2O7. I mean, the fastest way I can think of to do this is to plot it on your graphing calculator and then just plug in the 0.552 absorbance. 1 times 10 to the minus 3. Let's look at that. 0.558. Oops, that's not an 8. All right. We know it's going to be less, and we know that it's linear. How are we going to figure that out? Do I need to plot these? At time equals 0. All right, so each one of these gaps of time is 1.5 minutes. Is the absorbance changing linearly? I got to check that and see. So 0.78 minus 0.552. That's 0.228. Oh, it's not linear. Look what happens to the absorbance over time. I'm just taking the difference between the absorbances and look at how it changes over time. Is it changing by the exact same amount every 1.5 minutes? It's not.
No.
So it is not. So the one thing we do know about it is that the half-life is not constant. Right, because that Not first order. What is the difference between the next one? 0.390.
So could we use that justification, like you're saying like the difference between the 1.5 minutes and not linear, so that's why it's not first order, because that's like the question.
Yeah, that'd be so that would answer F, right? So F says a student claims that the data indicate that the reaction is first order for dichromate. Do you agree? And we could say no because it's not, the concentration is not changing at a constant rate, right? It's not, the half-life is not constant over time. And so it's not first order. Yeah, look, it goes down here, 0.081. So these are the differences I got between every two absorbents. But absorbance and concentration. Okay, so I can't see. So they said we don't have to draw any graphs and that we don't have to make any graphs. But the only way that I can think of to solve this is to plot the absorbance data with the one concentration point that the only way I can think of to solve it is graphically. So can you guys think of anything? Consult our equation sheet. And we don't know if it's, we don't know what the order is, so we don't know for sure which equations we could use. Natural log of the, I might have to go check the key on that one and come back and give y'all a little follow-up message on E. Let's come back to that one because I think we should be able to solve this without graphing it. Because this is the practice one that they put out for us for the real test, and they already said you definitely don't have to graph anything. All right, so we'll pause right there on E. We'll answer F with this, and then let's see if we can figure out the last one. Okay, what is the last one? We've got ethanol and diethyl ether, two similar looking compounds with very different boiling points. Identify the this is the easy one, right? So you have these two compounds. H. So that one versus this one. What are all the intermolecular forces that are present in these molecules?
LDF.
LDFs for sure. Both of them have London dispersion forces. What else? Well, really, the question
One of them has dipole.
One of them has dipole. Which one?
Ethanol.
Yes, for sure. It's polar. This is not symmetrical. Why isn't this one polar?
Because it's symmetrical.
That's symmetrical.
Yeah.
I think it's I think it's slightly polar because you got these two lone pairs on your oxygen. This looks super symmetrical, but if we build a model of it, it's not perfectly symmetrical. But clearly the forces are way higher in this one, right?
Yes.
The boiling point is way higher. And so the question says, which force is most responsible for the difference in boiling point?
Dipole.
This has all of the time.
It's not your dipole force. It is your very strong thing that we only get when we have a hydrogen bonded to an oxygen, a nitrogen, or a fluorine.
Hydrogen bond?
Hydrogen bonding. So H bonding is the main difference there. The force that's most responsible for the difference in boiling points for the BP diff. Because this one can and will hydrogen bond. And look, it's got a really high boiling point, not as high as water, but getting there. And then this one cannot. All of its hydrogens are on carbons, and things that have hydrogen on carbon, well, that's just everyday normal stuff that can't hydrogen bond at all. So they both do have LDF, and they both do have dipole-dipole forces. Even though this one looks really symmetrical, you don't forget about these lone pairs of electrons on oxygen that throw that off. And it is still symmetrical, but it's also not, the electron density is not symmetrical. The molecule has lovely symmetry, but it is polar. So they both have the, but only your ethanol has the ability to hydrogen bond, and that gives it the higher boiling point. All right, all of this was worth 1, 2, 3, 4, 5, 6, 7, 8, 10 points. How'd we do?
We did our
We
best.
did pretty
That's
well.
what I'm going to leave it at.
I think I only got 9 because I can't think of a way to solve this without graphing. But I'm going to look at the key and come back and share it with you. All right, any other questions?
No, I'm good.
Y'all like today's practice problem? It has all kinds of stuff in it.
It sure does have all kinds of stuff in it.
Yeah, not going to dispute you on that.
Yeah. Okay, well, we can send out another one and start fresh. Okay. Y'all have any more?
Bye.
I think I put in everybody's grades for those of you that did the second practice quiz, but when I reopened it, I haven't gone back and looked to see if anybody else finished. So
I finished that at some point this morning, like 1 a.m. or so. So that got.
well, I'll go back and look at those now. And we can go over, we might want to go over those practice ones that are in there, because I saw
Good idea.
a few things. Actually, one of them was a chemistry thing that a lot of people mentioned. And then not showing your work. So like if you have an easy problem, you have to find moles. You show your work. The readers are not, for this year especially, they're not going to be able to give you credit for work that doesn't work for your work.
So on the questions, like on the practice tests that were like we had to type, like it was just typing, because like some of them we could take pictures and put all of our work to it, but then some of them were like typing. So does that mean we were gonna have to type out like all of our work we can?
So you can't once you decide to either type or handwrite, you can't switch. Like you have to stick with that method for that whole question for all the parts. So it won't let you give like a hybrid, like part typed and part handwritten. And I honestly don't know what's going to be the best method for you guys. I tried it this morning, like to me it feels handwriting, and then have a Google Drive window open. Have a Google Drive window open, and send the pictures to your Google Drive. Okay, be careful. Love you. Upload it like from the pictures from your phone to your Google Drive, and then you can download it in. If your Google Drive is already open, it'll show up pretty much instantly, and then download it back into the document. But see, like that, even that takes like 3 minutes. I mean, it's not instant. And so I just don't know what's going to be the fastest choice for you guys, but I would love for y'all to open that practice test and try it out.
I think what I've been doing for the year practice test, I've been taking it on my iPad. So whenever like has this, whenever we have like all of our work and it says like upload a file or something, on my iPad, it gives me the option to like take a picture. And so like I can immediately take a picture with my iPad of my work, and it just immediately uploaded it. So I found that was pretty fast.
Okay, that sounds perfect, especially if you've practiced it and you know how to get there. Typing is pretty great, except for like it gets messy for trying to show your work in chemistry. There's a little handout in that slideshow of like things that you should type if you're going to type, and maybe we'll take a survey later on in the week, give y'all some time to try it out. But I am kind of curious about who thinks they're going to type their answers versus handwrite. Yeah. And honestly, like, I just don't